Our investigations of the ocean are, at its essence, just investigations of biological diversity. Whether we're studying the diversity of species, the diversity of geographies, or the diversity through time, we're trying to get a capture of an underwater world, to archive that, to understand it, and to communicate it. But studying diversity presents a number of challenges on land. How do we identify a species? How do we record accurate depictions of geographic variation? Or how do we archive what an ecosystem looks like today so we can compare it with that same ecosystem tomorrow? Those challenges that we have on land are only multiplied when we get to the underwater world. How do we keep track of what species live in a particular location? How do we compare an underwater world from one site to the next? And then how do we record faithfully what it looks like today for that comparison with tomorrow when our observations are often limited? They're limited by our access to these ecosystems. If we're swimming underwater, how do we write down sufficient information so that we can compare faithfully from geography to geography or through time? How do we archive information if our only samples come from occasional boat visits to this underwater world? How do we keep track of what we know? And then how do we share that information from one person to the next? Our scientific and management history has included a number of people trying to collect tons of great data. Monitoring professionals, scientists, and explorers, all keeping track of what they've seen across the world's oceans and trying to tell stories that span generations. As much as we've done a good job of this, we've lacked the ability to really translate, to see directly through one another's eyes, to look through time and across space in a way that's visual, in a way that contains all that fine detail that sometimes our memories forget. Large area imaging provides us an ability to capture more information, to share more stories, and to extend more of what we know from individual to individual and through time. Perhaps one of the best examples of this I know comes from the coral reef setting and comes from the seminal work of Dr. Jim Porter from the University of Georgia. Dr. Porter began studying coral reefs on the island of Jamaica along the north coast in the mid-1970s. Working with colleagues from Jamaica and the United States, he was interested in how the coral reefs of the north coast changed. He was able to document hyper-diverse coral reef ecosystems with ranging from the charismatic corals like you see here and all the infauna that live within that reef environment. But he began with a simple thesis that he wanted to investigate. That thesis being, how do coral reefs change? As he describes the story, he had challenges to even get financial support for his studies because most people believe that coral reefs didn't change. That the image that you see here is from 1976 is what the reef would look like in 1977 or 1980 and had looked like in 1960. But as we all know, coral reefs are not simple systems, and coral reefs are not static. He fought and found resources to complete one of the first photogrammetric studies of a coral reef from Discovery Bay, Jamaica. What he was able to do was to capture images, in this case, photomosaics. If you look close enough here, you'll see 8 different photographs that were stitched together to make one large image. And he went back to the same location year after year to document the patterns of variability, both across the location and through time. And what he captured was really a fascinating time series that captures something that is the coral reef story as we know it from Jamaica. From 1976 to 1980, we see evidence of the loss of the acroporids linked to the spread of the white band disease that spread throughout the Caribbean. So what was a forest of elkhorn and staghorn corals became something of a rubble field. with a few other taxa of hard corals remaining. We return in 1983. We see this boom of the long-spine sea urchin, Diadema antillarum. The sea urchin growing because its competitor of herbivores, the herbivorous fishes, their populations have been depleted because of the rising population in Jamaica and the intense push on the local fisheries. So with the rise of the sea urchin population, you saw a very clean reef landscape. But as many of you will know, 1983 did not bode well for the long-spine sea urchin. Later that year, an epizootic spread across the entire Caribbean basin, killing over 98% of all the Diadema antillarum from the entire Caribbean. So Jamaica, Discovery Bay, that looked like this, that had some corals remaining, and fine, clean calcium carbonate where the sea urchins had grazed, by 1986 was covered in algae. With the last herbivores gone, with those sea urchin populations depleted, we saw what used to be a coral garden be reduced to something more analogous to a phycologist's dream, an algal garden. Well, this time series really helps to bring home a story that probably most of us have heard before. A story of degradation and loss of the live stony coral community in the Caribbean. When we met Dr. Porter, he brought up this time series, shared with us some of this imagery, and we had the opportunity to go with him back to Discovery Bay to sample these same locations. And because of a very elegant collection of maps and a robust set of marking techniques, we were able to find the same exact locations that Dr. Porter had started sampling 40 years before. And we were able to image these same locations. Well, yes, image-based technology has increased from film to digital cameras, and from photomosaics to the generation of three-dimensional models. But the point holds that the imagery tells a better story than I do as swimming around and trying to tell you what happened. This reef environment that used to be covered in the acroporids, clearly still gone. The algae, still present. But what we saw there was evidence that some of the corals remained. Importantly, some of these core charismatic corals remained. What used to be a marine environment that had a bunch of corals now could be seen through time, across decades, spanning a number of different ecosystem states. Imagery has helped us to archive that information and to share it through the generations. Now, how do we conduct image-based surveys? How can we take a typical survey by ecologists, resource managers, conservationists, or restoration professionals and try to learn anything that can span generations? Well, we have to depend upon our growing ability to use technology. Here we see a typical scuba dive. Divers floating around trying to communicate with one another. We have people trying to enumerate the fish that live there, maybe deploying some equipment, and in many cases archiving what they see on a slate. But what we see on a slate doesn't necessarily capture all of the information. It captures what we see, what we wanted to write down, and what we opted to record. Were we able to record this shark coming behind one of the divers? Only if one of our surveyors was there to document it and write it on their slate. Would we be able to see the structure of this reef, its bumpiness, its topography, were we not to have measured it with a chain and tape, a profile gauge, or some other metric? The challenge that we have as practitioners who are trying to study these coral reefs is trying to find new ways to capture information that contains the information that we care about, be it the amount of coral that lives there, the amount of algae that lives there, the diversity of species, or the topographical complexity, but at the same time fitting within what we're constrained by, the operational constraints of being a scientist or a resource manager in the water. Large area imaging is one such tool that's giving us an ability to see further, to see wider, and to see more of what's on the bottom of the ocean. Through a simple approach of taking hundreds, if not thousands of photographs, we can create reconstructions of an entire natural ecosystem. Some call it a digital twin, some call it a photomosaic, and some call it a 3D model. But what I call it is beautiful. I'm able to capture through imagery this reconstruction of what was underwater in a particular location. We can tell stories about what we see here, and we can share those stories. We can discuss more detail about what's going on because we can experience it together. Now, scuba diving with a friend or a colleague can give you a similar ability, but for most of us, it's difficult to talk underwater. We can come up from a dive and discuss what we saw, but it's going to be tough to go reinterrogate what's there. Even more so if we want to collect quantitative data, we're constrained by the amount of time or the tools that we have to make that measurement in the water. With this digital reconstruction, I'm able to make a lot of those measurements. I'm able to discuss, and I'm able to spend more time exploring the diversity that is the coral reef. Now, what is photogrammetry and what can it tell us? Well, photogrammetry, as we'll learn, is simply the idea of measuring things based upon photographs. So if we take a 3D model, we can get down into the raw information that exists there, the photograph. If we zoom into a 3D model, you can see that this is a photograph. You can see that high detail that we can capture from digital photography. And we can see features we may care about. In this case, I'm circling all of the coral juveniles. In this case, let's call those juveniles any colony that's between 1 and 5 centimeters in diameter. Well, I can see that in a model that a 1 centimeter feature in a model that's 100 meters squared. If I do this enough times, I can find a lot of coral juveniles. I can map them out by their species, by their location, and I can learn a bit more of what's underwater. I can take a landscape that looks like this, that may cover something in the ballpark of half of a basketball court, half of a tennis court, and I can start to learn something more. I can measure. So let's take a tour of a coral reef. Let's take a tour of photogrammetry and think about what we might be able to learn from a coral reef based on imaging. In one location, I might be interested in different types of habitat. Where's the consolidated substrate? Where's the substrate that if there's a big swell event, it turns over? I can map that out. I can look for features to see where these different types of substrate exist. I can take this same location and I can map out the location of every juvenile coral, or at least those juveniles that I can sense based upon the photography that I began with. I can ask questions about which taxa like to live in different locations. Or I could simply ask the question, how many coral babies exist within this plot? All of these questions are bound by the details of the imagery I have and the quality of the reconstruction. But this is photogrammetry. This is ecological photogrammetry. Let me return to this site and think, well, I might care about where the babies are, but where are the adult corals? Can I work out anything about what lives in this location? Indeed, I can. With a little bit of patience, I can zoom in on this photograph, zoom in, zoom out, and I can identify individual coral colonies. In this case, I'm mapping out every coral colony by taxonomy. A different color is a different type of coral. And I can ask questions about these corals. I can ask about the size structure or the density, how many there are by species. Or I may ask questions about where do they live relative to one another. I can address questions about patterns of clustering or spatial competition. We can maybe learn something about the basic ecology or learn something about the patterns of growth that may be useful for restoration and conservation. Or I can take a look at this image and explore things I hadn't really thought about before. What if I were to think about where the algae live? We know that macroalgae are a big important part of our coral reef community. Well, where do they live? I can look at this landscape and maybe look for one type of algae. Call it the halimeda, the calcareous algae. And I can map it on this landscape. Well, just for your reference, the halimeda, we're talking about this group of seaweeds. We're looking in the Central Pacific right now. Calcareous algae grows a couple centimeters tall, and we can map it out. But when I map this out across a domain, I might see things I never thought I would have seen before. Look at this pattern that emerges. In this case, the two different colors are the distribution of the halimeda between two different years, sequential years. And between those 2 years, I see a similar pattern. When I open my eyes to this, I don't just see a random distribution of seaweed. Instead, I see polygons. My brain immediately goes to an image of a field of mud. When it dries and dries, it starts cracking and making these characteristic and sometimes beautiful patterns. But in this case, it's halimeda, and it's growing over a landscape that's approximately 100 square meters. These polygons have a characteristic scale of about 5 meters, 6 meters across, and are something we've never seen before. Because it's tough to see patterns at this large scale when you have to see everything when you're swimming around at the bottom. Spatial data provide us this ability to see things we'd never seen before. And the imaging, the photogrammetry, is the tool that's helping us to see more. Now there's plenty that we can learn about a coral reef from the spatial patterns that exist. But I think for a lot of us, we're in this field to understand how coral reefs are changing, what they're going to look like tomorrow. We know that there are myriad factors changing in a coral reef, whether it's the patterns of fisheries exploitation and use, whether it's the patterns of sewage discharge or other pollutants coming from shore, or the existential threat that is climate change. So can we? Well, how can we watch coral reefs change? Well, why not just watch it? With the advent of new technologies, we have this ability to literally watch coral reefs change in 3 dimensions. Or call it 4 dimensions. A 3-dimensional model that we can track through time is the closest thing I've ever seen to a 4-dimensional coral reef. In this case, we're watching a time series across a 5-year domain of the same location. It's like we're taking a tour through time. We can see that in the middle, this 2015 time point includes a bleaching event. We see that many of the corals bleached, and we can track their fates afterwards. We can start to think, what happened yesterday, what's happening today, and what's happening tomorrow. We can track diversity in a way that we never could before. And the important thing here is we can do this in multiple directions. We can rewind, we can explore, we can change the course of our views. We can try to remember what we saw during a scuba dive 5 years ago through that interrogation of imagery that we collected 5 years ago. And this is the excitement that new technologies in imaging and image-related software are providing for us. And what we can start to document are some very interesting patterns. We'll see patterns of loss, like this massive table coral flipping over, likely due to a storm event. But we'll watch patterns of growth too, like this field of acropora, of branching corals regenerating after getting knocked down. We can watch the life and death processes. And what's so important about that? Because for us to manage coral reef ecosystems, we have to know what's changing and how it's changing. And many times our observers, we ourselves as observers, may not be documenting everything we want to know. We might not even have the ability to measure with the same precision as the new technologies in photogrammetry offer. Can you imagine seeing 2 different years of a coral reef at the same time? Well, you're seeing it right now. And everything that's in green is new coral that didn't exist 1 year earlier. These table corals are growing like crazy, adding, say, 10 centimeters of radial growth within a 1 year period. We see some areas like this red that fell over in that 1 year period. Storm damage, perhaps, that's changing the structure of the reef. But we can start to document that heterogeneity, that change, that dynamicism that Dr. Porter introduced us to in Discovery Bay 40 years ago. And if we can start using more of these tools as a community, we can start to share these anecdotes. We can start to learn from one another and from one another's geographies. We can start to think, why is one coral reef perhaps growing faster than another? And we may be able to leverage some of that knowledge toward improved management or restoration efforts. Now we know that coral reefs are a dynamic place, and we know they're hypervariable. But to date, we spend a lot of time trying to find commonalities, or at least a common metric to discuss. How much coral cover, how much algal cover, how much crustose coralline cover. But sometimes in those simplifications, we miss that ripe complexity. We miss reference to the diversity that is a coral reef. And we miss that ability to tell the story that says, why is one location different than another? And based upon that story, be able to share with one another why we think that might be. I want to be able to take tours of the world's coral reefs. And I don't want that to be something that's linked solely to me or accessible only to a subset of coral reef professionals. I want to be able to hop from an island in Tonga over to an island in Micronesia with the click of a mouse. I want to be able to think about, why are my colleagues who work in Lanai in Hawaii thinking that, why are they seeing observations of rapid growth, whereas perhaps in the island of Pohnpei, we see individual coral colonies with a lot more stability. Perhaps it's because the corals are bigger or smaller. Perhaps it's because there's a history of competition with other taxa. Perhaps there's just some strange new feature that nobody's ever described before. I love being able to see different locations. And I want us all to be able to watch things change through time. We can document some things that may be dramatic periods of loss, like some of the devastating Central Pacific damage that came with the marine heat wave in the mid-2010s. But we can also watch areas where we see reefs growing. There are records of there being effectively no corals on the island of Moorea, the fore reef of Moorea, about 5 to 10 years before that imagery was collected. And in a beautiful time series, we can start to think about how a reef that had a bunch of recent recruitment of table corals could document a pattern of change. How could it grow back? Now we know that as professionals, we're going to be documenting a lot of dramatic change over the coming decade, 2 decades, century. But that change is going to be able to tell us a lot of important stories. That change will contain information about what is possible. We all fear for some of the troublesome futures that we hear are happening with coral reefs. But if you're like me, you hear some encouraging anecdotes of reefs that are growing, rebounding. And especially with the hard work of our restoration professionals who are taking some elements of reef recovery into their own hands, we may have some tools that allow us to see reefs grow. But I have a feeling that we don't know the answer. We don't have a silver bullet. There is no single solution that's going to lead us to the fixing of coral reefs everywhere. But I think with our common knowledge, and by sharing information with one another, and more importantly, by telling stories, by seeing the reefs that one another work in, we have an opportunity to take some serious advances to improve the livelihood of our coral reef communities. With this course, we're bringing together some folks who have been spending time working in the world of photogrammetry. And we're going to try to build our community, trying to see the world's coral reefs and to share this information. With this, I thank you and I welcome the course that comes ahead.